I hope you're able to hear me, right?
Yes, sir.
So we'll get started. So yesterday we were discussing the second part of fluid mechanics, right? That is, we were discussing a concept called as viscosity, that is the friction in fluids. So yesterday we saw what viscosity means. Viscosity is the property of a fluid by virtue of which an internal force of friction comes into play when the fluid is in motion and which opposes the relative motion between its different layers. Then we saw what is the cause of viscosity when you talk about a fluid which is moving on a fixed surface. So when the fluid is in contact, the fluid which is in contact with the fixed surface is going to be at rest. As you keep moving upwards, the frictional force, the velocity of the particles actually increases, right? So all these things we saw. So due to the friction that is existing between the layers, there will be a force which is coming in the opposite direction, which is called as the friction, viscous force. So yesterday, based on this particular concept, we also saw what is the formula for viscous force also. So in the name of a topic called as coefficient of viscosity, I think this is where we stopped because there was a power cut. So we saw a concept of coefficient of viscosity, which is called as neta. So with respect to the fixed surface, let's consider two layers, A and B. So if the layer B is at a distance x from the fixed surface and the layer A is at a distance of x plus dx from the fixed surface, if the layer B has velocity v and the layer A has velocity v plus dv, right, then it was observed that the frictional force that is acting between the layers, the viscous force, was observed to be directly proportional to the area of each layer, is directly proportional to dv by dx. I told you yesterday what does dv by dx mean. It's called as velocity gradient. So from this, when you combine both, force is observed to be directly proportional to A into dv by dx. So when you remove the proportionality symbol, the constant that we introduce is F is equal to minus neta into dv by dx. And this neta is what is called as the coefficient of viscosity. And the negative sign indicates that it is a resistive force. Right? So all these things we discussed. Where neta is called as the coefficient of viscosity of the liquid, it depends on the nature of the liquid and gives a measure of viscosity. So negative sign shows that the viscous force acts in the direction whom? Opposite to the direction of motion of the liquid. Right? So I hope you have made a note of all these points and it is in your mind. Right? Now, we will define the coefficient of viscosity in terms of viscous force. So for that, what we will do is, see, you have a formula like this. Minus neta into A into dv by dx, right? Now comes the question. Did I write only neta? Oh, sorry. Minus neta into A into dv by dx, right? Now observe guys. So I want to define the coefficient of viscosity. If I write only in terms of magnitude, F is equal to neta into dv by dx in magnitude, right? Now comes the other question. If I want neta to be equal to force, what is the value of A that I need to choose? A is 1 unit. And if I take dv by dx also to be 1 unit, okay, then if you take both of these values and substitute it here, F will be equal to neta. From this, how you can define coefficient of viscosity is, it is equal to the viscous force acting on the liquid between two layers of area of cross section 1 unit and the velocity gradient of 1 unit. Okay, so I'll show you. Coefficient of viscosity of a liquid may be defined as the tangential viscous force required to maintain a unit velocity gradient between its parallel layers, each of them of unit area. That is, if the area of P is 1 centimeter or 1 unit square, or I'll call it as 1 unit. Here also the area is 1 unit. That's what we call it as unit area. Then to maintain a velocity gradient of dV by dx is equal to 1 unit, then coefficient of friction is defined as the viscous force. Okay, make a note of this definition. Done?
1 minute.
Yeah, right. Shall I move on?
Yes, sir.
Now listen. So now let's see the dimensional formula of neta. So before we see the dimensional formula of neta, what will be the SI unit of neta? So to get the SI unit of neta, you can write it as F by A into dx by dv is equal to neta. Can I write it like this? When you just rearrange the equation. So what will be the SI unit of it? Force is measured in Newton. Area is measured in meter square. X is measured in meter. Velocity is measured in meter per second. This and this will get cancelled, which implies Newton second per meter square is what is the SI unit of neta. Right? So Newton can also be written as kilogram meter per second square, and you have a meter square in the denominator. That is kilogram meter inverse second power minus 2 is also the SI unit of neta. Right? Now what will be the dimensional formula of this? M L minus 1 T minus 2. Right? So this is the dimensional formula of coefficient of viscosity. So make a note of it. So I hope it is done. Now listen. So units of viscosity. The CGS unit of viscosity is dyne second centimeter minus 2 or gram centimeter inverse second inverse. So this unit gram centimeter inverse second inverse or dyne second per centimeter square, both put together, okay, is collectively called as poise. That is, if wherever you see gram centimeter inverse second inverse or dyne second centimeter power minus 2, that can be written as poise. For example, if we have Newton meter, and if the Newton meter is for work done, instead of writing Newton meter every time, we replace it with joule, right? In a similar context, this can be replaced with poise, and gram centimeter power minus 1, say second power minus 1, can also be replaced with poise. So 1 poise is exactly equal to 1 dyne second centimeter power minus 2. Okay. Now, what is the SI unit of neta? This I have already shown you. Kilogram meter inverse second inverse. and is called as decapoise, or it is also called as poiseuille. Remember, poiseuille is the name of a scientist. Have that in your mind. So the Cesius unit of coefficient of viscosity is poise, and the SI unit is called as decapoise or poiseuille. Deca means 10. Okay, you write it down. I'll tell you why it is called as decapoise. Now see. Dyne second centimeter minus 2 is called as poise. Newton second meter minus 2 is called as decapoise, or we call it as poiseuille. Right? So Newton second meter power minus 2, can I write it as 10 power 5 dyne 1 second. Meter power minus 2 can be written as 10 power minus 2 centimeter power minus 2. Right? It will be 10 power 5 into 10 power minus 4 dyne second centimeter minus 2. So 10 power 5 into 10 power minus 4 is 10. So Newton second meter power minus 2 is called as what? It's called as poiseuille. And 10 dyne second centimeter minus 2 is called as poise. So 10 times poise is what is called as decapoise.
Sir, could you go up a bit?
Yeah.
Sir, it's decapoise or what's this word, sir?
Poiseuille.
Okay, sir.
Got it?
Yes, sir.
Okay. So the relation is also shown here. Now, based on this, let's do a problem. Okay. Now see.
Sir, so the SI unit of viscosity is poise, sir.
SI unit of coefficient of viscosity, not viscosity.
I said the SI unit of the coefficient of viscosity is poise.
No, it is poiseuille. SI unit is
Okay, sir.
poiseuille. SI is
Okay, sir.
poiseuille. CGS is poise. Okay. Yeah.
Okay, sir.
We'll be using this. So let's try this problem. So there is a metal plate 5 centimeter by 5 centimeter. So area is given as 25 centimeter square. Let's rest on a layer of castor oil which is 1 millimeter thick. So dx is 1 millimeter. That is 10 power minus 3 meter. So 25 centimeter square is 25 into 10 power minus 4 meter square. Whose coefficient of viscosity is 1.55 Newton second meter power minus 2. So neta is equal to 1.55 Newton second meter power minus 2. Find the horizontal force required to move the plate with a speed of 2 centimeter per second. So dV is 2 into 10 power minus 2 meter per second. Right. So F is equal to what? Neta into A into dV by dx. So F is equal to neta is how much, guys? 1.55 into area is 25 into 10 power minus 4 into dV by dx, that is 2 into 10 power minus 2 divided by dx is 10 power minus 3. Substitute all the values, you will get the answer. I mean, calculate it, you will get the answer. Done?
So is it 77.5, sir? Into 10 power minus 3.
Yeah, it is. The answer is there. 0.775 Newton. 0.00775 Newton. Right? Next. So try this one. There is a square metal of side 10 centimeter. So when they have told square and side is given, indirectly area is given. So what is the area? 100 into 10 power minus 4 meters square. Is moving parallel to another plate with the velocity of 10 centimeter per second. So dV is 10 centimeter per second. Both the plates are immersed in water. If the viscous force 200 dyne and viscosity of water is 0.01 poise, what is their distance apart? So since here everything is given in terms of CGS unit, you can just proceed with CGS unit and find the answer. So F is equal to neta into A into dV by dx. Applied, you will get the answer. Done?
Yes, sir.
Next. 30th one. There is a flat square plate of side 20 centimeter. Again, area is given. Moves over another similar plate with a thin layer of 0.4 centimeter of liquid between them. A force of 1 kilogram weight. 1 kilogram weight is how many Newton? I already told you 1 kilogram weight is 9.8 Newton or 980 dyne. Moves one of the plates uniformly with a velocity of 1 meter per second. Calculate the coefficient of viscosity of the liquid. So F is equal to neta A into dV by dx. Applied, you will get the answer.
Sir, can you say again, sir? Your voice was breaking for me, sir.
Saying area is given, dx is given, which is 0.4. Okay, dv is given, which is 1 meter per second, and force is given. Force is 9.8 Newton because 1 kilogram weight is 9.8 Newton or 980 dyne. Calculate the coefficient of viscosity of the liquid. Substitute in this formula, one unknown, one equation, you will get the value of neta. Calculation part, I am leaving it to you. Got it? So these are all the problems. Now, let's do a small comparative study between viscous force and solid friction. So both viscous force and solid friction come into play whenever there is a relative motion, no doubt about it. Because both of them have the same objective of opposing the relative motion. Both oppose the motion and both are due to what? Intermolecular attraction. Okay. So what are the points of differences? We have seen what are the points of similarity. Points of differences. Viscous force is directly proportional to the area of the layers of contact, whereas when you talk about solid friction, it is independent of the area of the surfaces in contact. Okay, it depends only on the normal force. Secondly, viscous force is directly proportional to the relative velocity between the two liquid layers, whereas solid friction is independent of the relative velocity between the two solid surfaces. Thirdly, in viscous force, it is independent of the normal reaction between the two liquid layers, whereas in solid friction, it is directly proportional to the normal reaction between the surfaces. Remember, F is directly proportional to N there. Here, F is directly proportional to A and F is directly proportional to dV by dx. When you combine these two, you get neta as the, so neta into A into dV by dx as the viscous force. Here, when you remove the proportionality symbol, you will get mu, where mu is called as the coefficient of friction. Here, neta is called coefficient of viscosity, that is liquid friction. Guys, am I clear with the differences? Good. Okay. So variation of viscosity with temperature and pressure is not needed for you guys. Okay. So practical application, this also you can read it. This I'm giving it as self-study. The next one is Poiseuille's formula. Okay. So this Poiseuille's, we are going to see what is the statement of Poiseuille's formula, what are the assumptions used in the derivation of this formula. Derive this formula on the basis of dimensional consideration. Means this formula's derivation itself is using the process of dimensional analysis. Okay, so let's see what is the statement and formula. So this Poiseuille's formula mainly speaks about the liquids in motion, because we have already started fluid dynamics, right? Okay, so the volume of a liquid flowing out per second, this is the statement. So if you're able to calculate the amount of volume that is flowing per second through a horizontal capillary tube. So as of now, capillary tube means, have it in your mind. You have seen straws, right? You have used it. So straw is an example of a capillary tube. Capillary tubes are the one whose length is more compared to the thickness. Okay, as of now, remember it like that. Okay, so the volume of the liquid flowing out per second through a horizontal capillary tube of length L, radius R, under a pressure difference. Means, remember, if the pressure here is P1 and here it is P2, if the liquid has to flow from left to right, tell me which side pressure is supposed to be more, guys. So which side pressure is supposed to be more? I've asked a very basic question. P1 is the pressure on left hand side and P2 is the pressure on right hand side. Which side pressure is supposed to be more for the liquid to flow from left to right? There is a block. I'm applying force F1 here, force F2 here. If I want the block to move to the right, which force should be more?
Left.
F1.
Same logic, no? So pressure on the left hand side should be more compared to the pressure on the right hand side. If the pressures on both the sides are equal, the liquid inside is not going to move. So that is the reason why they are using the word under a pressure difference P applied across the ends of the tube. Okay, in this case, P1 minus P2 is the pressure difference, which is called as small p. Okay, so the amount of volume, V stands for volume, the amount of volume flowing per unit second is equal to what? Pi into P, where P stands for pressure difference, into r power 4 divided by 8 into neta into L. 8 into, what is the value of neta? What is neta? Neta is the coefficient of viscosity into L is the length of the capillary tube. And how is the tube supposed to be? It should be horizontal. Never underline this word. So this whole formula, pi into p into r power 4 divided by 8 into neta L, is what is called as Poiseuille's formula. Okay. Am I clear, guys? Am I clear or not?
So could you show the left hand side for a minute, sir?
This side. So this is the heading.
Yes. Sir.
Shall I show the right hand side now?
Yes, sir. Yes.
So I hope everybody has made a note of it. Right. So next we are going to see what are the assumptions under which this Poiseuille's formula is actually derived. So what are the assumptions used in the derivation of Poiseuille's formula? The first one is the flow of the liquid is supposed to be steady and parallel to the axis of the tube. So you know what is the axis of the tube? If the tube is like this, the horizontal line that is passing through the tube is called as axis. So liquid is supposed to flow. So it is like this. So liquid is supposed to flow parallel. It should flow in this direction. It should pass parallel to the axis. Next, the pressure is constant over any cross section of the tube. Means if you take a particular cross section, in that cross section, if you try to calculate the pressure at any point on the cross section, then it should be a constant value. Third, the liquid
Sir, can you
velocity.
explain the first point? Sir, can you explain the first point again, sir?
So I'm saying the flow of the liquid should be steady, okay, and it should be parallel to the axis of the tube. So
Sir,
this is the
liquid
axis.
should be steady in the sense what, sir? Steady in the
Steady,
sense.
steady means, make a note of it. Steady means, I'll explain this word steady when it comes to the next part of the chapter. Okay, I'll wait. Okay, I'll explain it now itself. Listen. See, this is how the liquid is flowing. Okay. The liquid is flowing from left to right. Imagine it like this. Now I'll take 2 points. A, B. Okay, one more point, C. If the velocity, see, if I talk about the liquid particles, concentrate, I'm using the word liquid particle because this liquid will be made up of many molecules. Many molecules of H2O will be there in it. If the particle at this point has velocity v1, at some point, let's say x, okay. When the first particle is reaching the point x1, if it has velocity of va, then there might be some other particle over a point y which is having velocity v2, right? So v1 and v2 are not same. Obviously, they'll be different. So what should happen is, when the particle at point y, which is having velocity v2, when that particle is reaching point a, if it also has the same velocity va, means at every point, whatever is a particle that is reaching, if it is reaching that particular point with the same velocity, then this kind of a motion is said to be steady motion, steady state condition. Okay. Similarly,
So the water should flow at the same velocity till then, sir.
No. At a particular point, the velocity should be constant. So what I'm trying to say is, listen. This is the first particle. This is the second particle. Now, when the first particle is reaching point B, what will be its velocity? Let it be VB. So when the second particle is reaching B, that should also have the same velocity VB. Means at a particular point, n number of particles are reaching, means when those n number of particles are reaching a particular point, the velocity of all those particles at that point should be a constant. Similarly, the first particle, when it is reaching the point C, if it has velocity vc, then the second particle, when it's reaching point C, should also have the same velocity vc. If this kind of a condition, I'm not trying to say velocity at every point is the same. Velocity of every particle reaching a particular point will be the same. So at a particular point, the velocity of every liquid molecule is the same. This kind of a motion is called as steady state motion. In practical basis, it is very difficult to achieve this. So that is why we call it as an assumption. Okay, this kind of a liquid flow is called as ideal flow, which is actually not possible. That is what is meant here. The flow of a liquid is steady and it is parallel to the axis of the tube. Secondly, the pressure is constant over any cross section of the tube. So if you take the cross section of a tube, so how will when the tube is circular, if you take any cross section of the tube, you will see this kind of a circular part. So on this circular part, if you calculate the pressure of any particular pressure at any particular point, the pressure at every point on this cross section should be the same. Third, the liquid velocity is 0 at the walls of the tube and increases towards the axis. So we know one concept, right? When we saw the cause of viscosity, the fluid which is in contact with the surface will have how much velocity?
What's the
The
question?
fluid which is in contact with this fixed surface.
It will be 0, sir. It will be at
It should be
rest.
0. That is what they're saying. The liquid velocity is 0 at what? At the walls of the tube. So this is one of the walls of the tube. This is another wall. So both the walls of the tube are fixed, right? So try to understand the difference. When we saw the case here, it was only fixed surface at the bottom. That is why here the velocity is 0. Whereas when we are seeing this case, you have fixed surface at 2 points, top point and the bottom point. So at both those points, the velocity is 0. Okay, but as you keep moving towards the axis, their velocity keeps increasing. That is, as you keep moving away from the fixed surface, the velocity should increase. That's what the cause of viscosity is telling us, no? Similar, lastly, the tube should be held horizontal so that there is no effect of gravity. So here, the liquid is not flowing under the influence of gravity. Rather, it is flowing under the influence of whom? Under the influence of pressure difference. If all these 4 points are satisfied, then you can define Poiseuille's formula. Okay. Let's see what is the derivation of Poiseuille's formula. So what does it state? You guys would have written it, no? Amount of volume flowing per unit time is equal to pi p power 4, sorry, pi p into r power 4 by neta into
I.
Neta into, it's not I,
I.
it is L. It is L. Sorry, I forgot 8. By 8 neta into L. Okay. So generally this V by T is written as Q, which is called as the rate of flow of liquid. Yesterday I told you, no, when do you use the word rate? When something is measured with respect to time. Here the amount of volume flowing per unit time is called as rate of flow of liquid. So pi p power 4, p into r power 4 by 8 neta into L. Did I delete that page? Now listen, guys. So can I say, so you remember dimensional analysis, right? Q is directly proportional to P power A. Q is directly proportional to R power B. Q is directly proportional to neta power C, and Q is directly proportional to L power D. So when you follow the dimensional analysis process, what are you supposed to get the value of A, B, C, and D as? A should come out as 1, B should come out as how much should it come out as?
4,
4. Neta should come out as
1,
-1. And L should come out as
-1.
-1. Okay, let's try to see. So Q, when you combine, is directly proportional to P power A, R power B, neta power C into L power D. But what is Q? Q is volume by time is equal to some constant. The constant should be dimensionless into P power A, R power B, neta power C into L power D. So what is the amount of volume flowing per unit time? So left hand side's dimension should be equal to right hand side. So dimensional formula of V by T should be equal to K into dimension of P power A, dimension of R power B, dimension of neta power C into dimension of L power D. What is the dimension of V by T?
Meter per
LQ.
second square.
No, that is SI unit. It is not meter. V stands for volume. It is not velocity.
Volume, sir. Sorry, sir.
Yeah. So it is L cube divided by T is equal to K into, what is the dimensional formula of pressure? M. Pressure is force by area. Force is MLT minus 2. Area is L square. So it will be ML minus 1 T minus 2 to the power A. Okay. R is how much? L power B. Neta. We have already seen the dimensional formula of neta. What is it? You can look at it and tell me.
ML minus 1, T minus 2.
Is it same as pressure? It is T minus 1, no? Now tell me. So this will be M power A, M power A plus what? M power A plus C, L power minus A plus B minus C plus D, and T power minus 2A minus C. Okay, this is L3 T minus 1. So A plus C is 0, minus A plus B minus C plus D is 3, minus 2A minus C is minus 1. Find out the value of A, B, C, D and tell me first. So A plus C is 0. So B plus D will come out as 3. If I substitute it here, B plus D will come out as 3. So solve these two equations. You will get minus A is equal to minus 1. So A will come out as 1. If A is 1, C is minus 1. Okay, now we need to solve. Did I leave B anywhere? So B plus D is 3, right? Okay. So actually what we could have done is, since R and L belong to same family, so we could have actually taken 1 minute, a small correction guys. We could have actually taken as P by L to the power A. So P by L, to take it power A, P by L power A, then this L power D is not needed because you cannot solve this. B plus D is 3 means 2 unknowns, 1 equation, it's not possible for us to solve. So D will not come.
That means dimensions are also changed, no, sir, for PA by
Yes.
U.
So here it will become L power minus 2. So I'm making all the corrections, L power minus 2. So it will become L power minus 2A plus B minus C. So T power minus 2A minus C, right? So A plus C is 0, okay. Minus 2A plus B minus C is 3. And minus 2A minus 7. So A is 1, C is minus 1. So take all the things and substitute it here. So minus 2A minus 2 into A is 1 plus B plus 1 is 3. So B minus 1 is 3, B will be equal to 4. So what will be the answer? V by T will be equal to P by A to the power 1, R power 4, neta power minus 1. So P by L power 1. So it will, K is there. So K into P into R power 4 divided by neta into L. The value of K is experimentally found out. And what is its value? K will be 1 by 8. So if you substitute this 1 by 8 here, it will be P into R power 4 divided by 8 neta into L. Got it? I
Yes,
hope it is
sir.
clear, guys. Yeah. So I'm moving on to the next concept. So what we saw till now is Poiseuille's formula. Okay. The next important one is called Stokes' law. So there are two more topics in viscosity. One is called Stokes' law, and the last one is called as terminal velocity. Okay. So we know when Archimedes principle comes into picture, right? When do you speak about Archimedes principle? How will you know that at this point there will be a buoyant force that is acting?
When an object is floating or shows some resistance.
So what should happen? No, here there is no resistance at all. Resistance comes into picture only when it is okay. You're trying to say resistance to go inside the liquid.
Yes,
right?
like for sinking.
Okay.
Instead of sinking, a resistance.
Okay, it's floating. Okay, I can take it like that. So what I can say is when a solid comes in contact with a liquid, can I say it like this? When a solid comes in contact with a liquid and it is coming in liquid with it is coming in contact with the solid is coming in contact with the liquid and it is floating. At that point, I will understand that it is going to have something called as buoyant force and all those things. So Archimedes principle comes into picture. In a similar way, if there is an object which is falling through a liquid, mean in the sense, here the object is actually trying to move through the liquid. When it is trying to move through the liquid, what will happen is it will experience a viscous drag. And the Stokes law mainly speaks about the viscous drag that is experienced by an object that is falling through a fluid. So let's read what it is. So when an object falls through a viscous fluid, the layer of the fluid in contact with the body moves with its velocity. So what they are trying to say is, so if I have a liquid like this, okay, and let's say there is a sphere that is falling into the liquid. So it will have velocity in the downward direction, right? So there is this part of the solid is in contact with the liquid, right? So when this object is moving with a velocity v, the liquid which is in contact with this object tangentially will also have the same velocity v. That is what they're trying to say. The layer of the fluid in contact with the object moves with the velocity v. So what is the layer which is going to be in contact? That is the tangential layer. However, the fluid at larger distance from it remains at rest. Means from here, if I talk about the fluid at this point, it is going to still be at rest only. Okay. So due to this, what will happen is there will be a relative motion between the different layers of the fluid itself, because if I take this as first layer and the farther layer as second layer, the first layer is having velocity v, which is equal to the velocity of the ball itself. But the layer 2 does not have any velocity. So you can always define a non-zero relative velocity between them, because each layer is having different velocity. As a result, what will happen is the object starts experiencing viscous force, which tends to retard the motion. This retarding force increases with the increase in velocity. So as the object is moving, when its velocity is trying to increase, the amount of resistive force tangential, the amount of resistive tangential force it is going to experience will also increase. Okay. And that increase is, a minute. Yeah. So the retarding force increases with the increase in velocity of the body. Now we are going to see what is the actual force that is experienced by a sphere which is moving inside a liquid of viscosity neta. Now comes the Stokes law into picture. So according to Stokes law, what will happen is the backward viscous force acting on whom? On a small spherical body of radius r moving with uniform velocity v through the fluid of viscosity neta is given by F is equal to 6 pi neta into r into v. This is called as Stokes law. So this is the amount of viscous force experienced by the solid. So make a note of it. Okay. Now we will see the derivation of Stokes law. This derivation is also based on dimensional analysis only. So what happens is the viscous force F acting on the sphere moving through the liquid is observed to be dependent on the coefficient of viscosity of the liquid, the radius of the spherical ball, and the velocity of the object. Okay, so it is dependent on coefficient of viscosity, radius of the spherical body, and the velocity of the body. So I'm going to show you the derivation of C. So F is directly proportional to neta power A, R power B, and V power C. So F will be equal to K times neta power A, R power B, and V power C, where K is a dimensionless constant. So the dimensional formula of F will be equal to K into dimensional formula of neta power A, dimensional formula of R power B, and dimensional formula of V power C. What is the dimensional formula of F? ML minus 1 T minus 2 is equal to Dimensional formula of neta, ml minus 1 t minus 1 the whole, sorry, here it is ml t minus 2 power a. R is L power b and v is lt minus 1 power c. So it will be m power a, L power minus a plus b plus c, and t power minus a minus c. So a will be 1, minus a plus b plus c will be 1, and minus a minus c will be minus 2. So when a is 1 substituted here, minus 1 minus c is equal to minus 2, c will be equal to 1. When a is 1 and c is 1 substituted here, b will also be equal to 1. So what will be the value of f? F will be equal to k times neta rv, and this k is found out to be 6 pi. So 6 pi neta rv is the viscous force experienced by the solid. It is not by the liquid. So it is the viscous force experienced by the solid, a small sphere of radius r, which is moving with the velocity v, inside a liquid of coefficient of viscosity neta. Actually, if school was there, you would have actually done this experiment in the lab. Is that clear? So this is called as Stokes' law. So last concept that is left out in viscosity. Okay, viscosity is a part of the chapter. The last concept left out in viscosity is terminal velocity. This we can see tomorrow. Okay, so this will be the formula. We will see it tomorrow. Okay, I hope it is clear, right? So today we discussed about the coefficient of viscosity. We discussed Poiseuille's formula and Stokes' law. Revise all those concepts. Tomorrow's class we will see terminal velocity. Okay, just wait for a minute. Don't leave.